Hello everyone, welcome to Physics 205. So this video is actually going to go over the solutions for the in-class practice for the graphical methods of vector addition and vector subtraction. Okay, so this first question says the magnitude of two vectors A and B are 12 units and 8 units respectively. What are the largest and smallest possible values for the magnitude of the resultant vector, which we're calling R, which is A plus B, and then use graphical methods to explain your answer. And in particular, I want you to use the scale factor. 1 unit is 0.5 centimeters. Okay, so if you think about this, right, if we have some vector A, say it looks like this, and then vector B, let's say it's like this, 8 units, a little bit shorter, right? So we know A is 12 units, so just I'll call it 12, and then B is 8 units. It's 8. And we want to add these together so that we get the largest possible resultant vector. Well, if you think about this, right, the only way that will work, if you want the largest possible resultant magnitude, is if these two vectors are added such that they're pointing in the same direction, right? They have the same direction. So if I do this, if I start with A, I'll just do this graphically, and then we'll do it out on the paper more carefully. So this is A. And if I take the tail of B and add it to the tip of A, now if they're pointing in the same direction, it's going to add it like that. And then my resultant vector will be from the tail of the first one, so tail of A, to the tip of B. So it'll be this. So again, that's the only way that you're going to have the largest magnitude for the resultant vector is if A and B point in the same direction, right? If they didn't point in the same direction, let's say B pointed, like this, downward. Then if you did A plus B, so in this case, if I do A plus B, so I'm moving the tail of B to the tip of A, and then I draw my resultant from the tail of A to the tip of B, I'm going to get a magnitude, right, the length of R, which is smaller, okay? So the longest it can possibly be is if they're pointing in the same direction. Okay, and then, and I'll do this on the paper in a second. Let me describe the shortest, because we also want to find the smallest magnitude, right? The largest and smallest possible values of the magnitude of the resultant. Well, again, if you think about this, the smallest magnitude is when vector B points in the opposite direction of vector A. So if I were to take A, I'll just draw it in the same direction. And then let's say B pointed in this direction. And it has a magnitude of 8, right? So it's opposite. And then if I draw my resultant from the tail of the first to the tip of the second one, that's the smallest possible magnitude I can get for R, right? If A and B are in the opposite direction. Because any other direction for B, I'm going to get something that's larger for R, right? So that's the smallest it can be. If they're pointing in the same direction, that's the largest that it can be. Okay. And we want to do this on the paper, in particular, using this conversion factor where 1 unit is equal to 0.5 centimeters. Okay, so actually let me do those conversions right here first so we can figure out how long to draw these. So if A is 12 units, and 1 unit, which I want to put on the bottom here so it cancels, is equal, what did I say, 0.5 centimeters. Then if you multiply that, you're going to get 6 centimeters, right? And then B is 8 units. And again, if I use this conversion factor, 0.5 centimeters over 1 unit, that's going to give me, I guess, 4, right? 4 centimeters. Okay, so that's that's how long I need to draw these things. All right, so let me actually solve this now using the graph paper. Okay, so I'm going to start by drawing vector A. It doesn't matter what direction, I'm just going to draw along the x direction. So remember, in order to get the longest magnitude of r, we want them in the same direction. So I'm going to have both vectors pointing in the positive x direction. And A was, what was the magnitude? Let's see, it was 12 units, which ended up being 6, right? 6 centimeters. So it'll look something like this. So this is A. And then B, I'm going to put the tail of B at the tip of A, and that was 4 centimeters long. So that's something like this. So then if I want R, I got to go from the tail of the first to the tip of the last one. So that's going to be something like this. I'll just draw it next to it so you can see this better. And then if I measure that, I'm going to get, of course, 10 centimeters. This is B. This was R now. So the magnitude of R was 10. Centimeters. And if I convert back to units, remember 1 unit was 0.5 centimeters. If you work that out, 10 divided by 0.5 is like 10 divided by half, which is 10 times 2. So that's going to be like 20 units. So that's the answer. So R, the largest possible magnitude R could have is 20 units. And then with the subtraction, remember they had to go in opposite directions, right? So if we start with A, so again, that was 6, right? So that was 6, like this. That's A. Then if I put the tail of B at the tip of A, and I want to go backwards now, right? Because I want them in opposite directions. So I need to go back 4. So something like this. That's B, right? Going backwards. And then finally, R goes from the tail of A to the tip of B. So that would be like this. I'll just draw it next to it. So this is R. And then if you measure this, it's 2 centimeters. So the magnitude of R is 2 centimeters. But I want to convert that back to units. And I know that 1 unit is 0.5 centimeters. So if I worked it out, 2 divided by 1/2 is 4. So it looks like the smallest magnitude that R can have is 4 units, right? And that's when A and B are added such that they're in opposite directions. Okay, great. Let me go back to the iPad for the next question. Okay, so in this question, it says a jogger runs 100 meters due west, then changes direction for the second leg of the run. At the end of the run, she is 175 meters away from the starting point at an angle of 15.0 degrees north of west. What were the direction and length of her second displacement? So we're looking for that second displacement vector. Let me sketch this out first, and then we'll do it carefully on the graph paper. And for this problem, we want to use the scale factor that 1 centimeter is 10 meters. Okay, so I need a bunch of room here because I'm going mostly west. So let's say this is my coordinate system. So first, the vector is going west. Let me draw that a little better. So something like this. I'm going to call that D1. Then she changes direction. And actually, it'll be in this direction. I'll draw it right now. It'll be something like this. I'll call this D2. We don't know what this angle is, theta. We need to find it. But we do know that the resultant, if I add these two together, the resultant displacement was, so from the tail of D1 to the tip of D2, so something like this. Those should meet right there. And then this value we're given, right? So R here is 175 meters, and then this angle is 15 degrees. Okay, and we know D1, the magnitude of D1 was 100 meters. Okay, an angle you could say is 180 degrees, right? Because it's due west. So if I measure from here, it'd be 180 degrees, like due west. So given all that information, I want to find the second displacement, D2, right? I want to find the magnitude and then the angle. Well, if I do this graphically, right, and do this carefully, then to get the magnitude of D2, I can just measure the length and convert back to meters. And then to get the angle, I can just measure it with the protractor, okay? So the unit conversion factor we want to use here is 1 centimeter is 1 centimeter is 10 meters. So let's see how long we need to draw all these. So D1, if this is 100 meters, and I know that 1 centimeter is going to equal 10 meters. So if you worked it out, right, meters cancel, looks like we're going to get 10. So I need to draw that one, D1, 10 centimeters long. That's the one that's like due west. And the other one that we know is the resultant R. That magnitude is 175 meters. And again, if we use this conversion factor, then that's going to be 17.5 centimeters. And that should allow me, once I draw this out carefully, to figure out the magnitude and direction of D2. Okay, so that's what we're trying to figure out. All right, let me jump on the graph paper to do this problem. Okay, so I'm going to start by drawing D1, and I know D1 is at 180 degrees, right? So due west, and the length is going to be 10 centimeters. So something like this. Right, so that's D1. I don't know D2 yet, but I know R is going to be 15 degrees north of west. So if I put my protractor there, I want this to be at 15 degrees. So something like this. And that length is going to be 17.5. So here's 15. And I need to do another 2.5. I'm barely going to make it here. So that's going to be R, right, where this was 15 degrees. Okay, so now D2 must have been this vector, right? That goes from here to here. So if I start at the tail of tip of D1 and go out, that's going to be D2. So if you measure the length of this, it looks like it's pretty much around, it's hard to read this on the video here, but it's around 8.3 centimeters. So D2 around 8.3 centimeters. And then if I convert back to meters, well, I know there's 10 meters in 1 centimeter. So that's going to be like 83 meters. And then to figure out the angle, I can just measure this with a protractor. And it looks like it's pretty much around maybe 33 degrees. So this angle here is like 33 degrees. But it's going to be north of west, right? Because I'm using the reference angle in that second quadrant, so north of west. So that's the answer, right? So D2, that displacement vector, had a magnitude of 83 meters at 33 degrees north of west. Okay. Next problem. Okay, in this question, it says each of the displacement vectors A and B shown in the figure below has a magnitude of 10 meters. Use graphical methods to find A plus B, A minus B, and then B minus A. Okay, use a scale factor of 1 centimeter equals 2 meters. So first, let's figure out what the lengths are going to be. So both A and B have magnitudes of 10 meters. And then if I use this conversion factor, 1 centimeter over 2 meters, then it's going to be 5 centimeters long, right? And they're both going to be 5 centimeters. Okay, I'll get on the graph paper in a second, but to get an idea of what this is going to look like, if we do A plus B, let me just like sketch this out here. So I want R is equal to A plus B. So in this case, I start with A. Let's look something like that. And then at the tip of A, I'm going to draw B, which is going straight up, right, 90 degrees. Sometimes if you want, you can draw like a new little coordinate system in here. And then B is at 90 degrees, same length, right, because it has the same magnitude. And then finally, R will look something like this. If I go from the tail of A to the tip of B, that'll be R. And I can measure the length, I can measure the angle. Okay, if I do, what's the next one? A minus B. So remember, A minus B is the same as A plus negative B, right? A plus the opposite of B. So in this case, if I started with A again, that's going to be in the first quadrant. And then if I add negative B, remember if B is pointing straight up, negative B is going to be pointing in the opposite direction. It'll be straight down. It'll be like this. And then my resultant will be, I guess, in this fourth quadrant now. So it'll look something like this. So that'll be R. And again, I can measure the length and I can measure the angle. And then finally, if I want B minus A, I'll do over here. That's the same thing as B. I start with B and I add the opposite of A. So if I sketch this out, I'm going to start with B, right, which is straight up like this. That's B. And then if I add the opposite of A, since A is coming out at 30 degrees like this, it's going to go the opposite way, right? If it's 30 degrees like this, then negative A will look like this, where this is 30 degrees. So it'll look something like this. And then finally, the resultant vector is going to be in that second quadrant, right? If I go from the tail of B to the tip of negative A, that'll be my resultant R. And again, I can measure the length and I can find the angle here just by using the protractor. Okay, so now that we know how to do it, let's actually do this out on the graph paper. Okay, so in the first case, it was R equals A plus B, right? So I had to draw it was what, 30 degrees. So something like this, and the length would be what, 5, right? 5 centimeters. Right to there. And then if I start at the tip, so that's A. If I start at the tip of A, I want to go up 90 degrees, right? Straight up vertically, something like this. And that was also 5 centimeters. I'll just go from like 10 to 5 here. So like this. That's B. And then finally, R goes from the tail of A to the tip of B, right, to add them together. So that'll look something like this. And this is R. So to get the magnitude of that, I'm going to measure this. Again, it's hard to read this on here, but it looks like it's around 8.6. So R is around 8.6 centimeters. And if I convert back to meters, right, the real world units, remember it was 2 meters is 1 centimeter. So that'll be 17.2 meters. And then to get the direction, I just simply measure this angle. And pretty much it's around 60 degrees there. So the angle, so this angle is like 60 degrees. This angle right here was just 30, right? For A. So this is going to be 60 degrees. So that's it. So that's the magnitude and direction. So R is equal to 17.2 meters at 60 degrees. Okay, the second one was A minus B. Well, let's see, A minus B. So again, I'll start with A. That was at 30 degrees. So this is going to be R equals A minus B. That again was 5, right? 5 centimeters. Something like that. This is A. And then remember, minus B is going to go straight down. Right? If B is going straight up, minus B is going to go straight down. That's also going to be 5 centimeters. So this is minus B. And if I add them, right, if I go to the tail of A to the tip of minus B, it looks something like that. So that is A minus B. Now to get the magnitude, I'll measure this. And it looks like it's pretty much around 5 centimeters. So R here is 5 centimeters. I'll convert back to meters. So remember, there's 2 meters and 1 centimeter. So that's going to be 10 meters. And to measure this angle, It looks like it's around 30 degrees south of east. So this angle right here is 30 degrees. So then R would be 10 meters at 30 degrees south of east. Right, and again, I have to add that south of east to know that I'm in the fourth quadrant. The other way you could do the angle is you could just give this angle starting at the positive x and going all the way counterclockwise. And that would be 360 minus 30. So that'd be what, 330 degrees. And you could just give that angle directly, and it's assumed that you're measuring from the positive x counterclockwise. Okay, and then finally, the last one was B minus A. Okay, so the last one here, I'll do it up here. R is B minus A. So now I start with B, that's going straight up, and it's 5 centimeters, so something like this. And remember A, so I'm gonna draw like a new little coordinate system in here. Just dash it in a little bit, kind of running into the other graph. So if A was 30 degrees above the positive x-axis, right? So in this direction, that means negative A is going to be 30 degrees below the negative x-axis, right? It'll be like in this direction. So something in that direction. And in that, again, its length is going to be 5 centimeters. Or something like this. Right, that's negative A. So B plus negative A, well, the resultant is going to be from the tail of B, from the origin to the tip of negative A. So like this. And if you measure that, it's pretty much around 5 centimeters again. So I'm going to say it's 5. So R here is 5 centimeters. So if I convert back to meters times 2 meters or 1 centimeter, that is again going to give me 10 meters. And then if I measure this angle, I think it should be around 30 degrees, but let's double check it. Yeah, it's right at like 30 degrees, right? If you extend that line out, it goes through here, 30 degrees. Okay, so this is going to be 30 degrees. So that means R here is 10 meters at 30 degrees north of west. Right, and that would be it. Or if you wanted to give just a single angle, you could have given this angle from the positive x counterclockwise. So that would be what, 180 minus 30, which is 150 degrees. Then you could say R is 10 meters at 150 degrees, and that would be fine. Right, either way, as long as we know that we're in that second quadrant. Okay, great. So that's it for this in-class practice.